Ladies and gentlemen, I'm very honored to be here. I'm very thankful to the Croatian Society of Geotechnical Engineering for inviting me or for selecting me to deliver 15th Nonveiller Lecture. But when I saw the last picture in '98, about 10 years ago, I was much younger, as you see. Years sometimes affect us, unfortunately, even though we may want it or not. Today, I would like to talk about what we have experienced in Istanbul and how we approach the problem. As an engineer, we always have enormous problems in front of us, and the questions we have to ask, for example, what can we do? So, the first question that I would like to answer is, why do we need microzonation? The purpose of the microzonation, of course, is to minimize the damage, the eventual purpose. But microzonation is a geotechnical and geological issue. First, I would like to demonstrate what I mean by microzonation. That means the earthquake characteristics that are affecting our structures are changing based on the geotechnical conditions, based on geological conditions within very short distances. So we cannot take Zagreb or take Istanbul, for example. We cannot design everything with the same level of earthquake input. So what we did, we were lucky. Sometimes you are unlucky if you have a large earthquake, like '99 earthquake, but you are lucky as an academician because then the government agrees that earthquakes are important and they try to invest in research, in applications. For example, this is one of the results of the '99 earthquake. We convinced the municipality that Istanbul is next on the line. I will show you, but I would also suggest at this point of time that if you haven't seen Istanbul, you better see it quickly. Because next time, I don't know. So this shows the first microzonation section of Istanbul done by our Japanese colleagues. Oyo actually did professionally, and this is an area you can see from the Eminönü, where Topkapı Palace is located, all the way to the airport, those of you who have been to Istanbul. And we have a mesh size of 250 by 250. We drilled around 3,000 borings, and we did extensive amount of geophysical and geological investigations. And for example, this is the mesh size. We have around 2,900 meshes, and we have geotechnical data in all of them. In addition, we have what we call a rapid response network. That is a strong motion located on the free field that would record the earthquake in cities like Istanbul. As you may know, the population of Istanbul is now 16 million. It's going to be 20 million in 5 years. So one of the big problems is that as soon as we have an earthquake, we have to point or we have to locate where is the highest damage so that teams, rescue teams can go there. In Istanbul, we have a very large area, as I will show you a little bit later. And of course, the rapid response network, we have around 200 stations distributed all over the Istanbul. The data will come, and in 5 or 10 minutes, we will be able to understand. Of course, we have the building inventory also. We will be able to understand where is the highest damage, and so that we can send our rescue teams there first. So if you look here, we have one advantage of this. Even though we were lucky, we recorded some earthquakes. As you see, this is one of the early earthquakes in 2008. As you see, even though there is about 55 stations in that area, but all of them do not operate all the time due to many different factors. But you would be able to see even the accelerations are low. They are changing from one location to the other, and the distance between these instruments is not more than 1 kilometer. Now, this is the other one. It's a distant earthquake of a larger magnitude, but you can still see that there's a significant variation in east, west, north, south from one location to the other. And this was the latest one. It is the strongest earthquake that introduced or excited around 2% milli-G or 2% G in the bedrock elevation, and you can see that the variability is still existing. On the other hand, if we look at them, we can see that by using a very simple site response model, shake, those of you who are involved in soil mechanics may have an idea, and you can see that if we know the soil profiles as we do, we can automatically model or predict what may happen in the long run. Here are some of the results in east-west, north-south direction of the strongest earthquake, and you can see that modeling to a certain extent within the engineering approximation can take care of what may happen in the long run. Now, in terms of spectra, the spectra is one of the things that we use for designing our buildings, acceleration spectra. The simplest approach is based on acceleration spectra. These are the variability in acceleration spectra during the recorded last earthquake. You can see acceleration spectra varies significantly from one location to the other, which indicates that we have to design the buildings accordingly. What can we do? If you look to our model, the simple one-dimensional shake, you can see that we can model to a certain extent, of course. You have to always remember there are uncertainties in the soil profile, there are uncertainties regarding the model that we use to analyze, but eventually we have some engineering ballpoint. And here, in 3 locations, you see the predictions, or the modeling, not predictions. The modeling is within the engineering approximations. Now, why? Sonia showed you some pictures from the Gölcük. I will show you some pictures from 99 earthquake too. This is the Gölcük area. You can see that most of the buildings is almost completely demolished. The second picture shows you that the damage is significant here in the section, but in the other sections, it is not so significant. It is maybe due to the design of the building, which I don't think. It's most likely the changes in the site conditions. And one more time, if we go, then you can see the center of the Gölcük. You can see that newly built mosque or newly built building and the mosque survived, while all other buildings, which were like 4-story, 3-story buildings, demolished completely. So site conditions actually played a very important role. Now, if we go to one more picture, now we are in Adapazarı, you can see the same earthquake, almost same distance, but there is no damage. The reason that there is no damage is not because the buildings are built better. It is because the site conditions, to a certain extent, minimized the earthquake input. So what can we do? Now, some people may believe that I'm just talking about small earthquakes, but let's go to look to Japan. One of the big earthquakes in Japan, 6.8, and you can see now Japan has million instruments. In Istanbul, we have only 150. In Japan, they have in the order of 2,000 strong motion stations, and also downholes, as we had. And you can see that this is one of the earthquakes. If I enlarge the picture, you can see that the peak accelerations actually are varying from one location to the other, and if I build one more time, you can see that they are changing radically from one location to the other. So somehow we have to analyze the site conditions and make sure that everything is okay. Now, one of the things that we had in Istanbul after the earthquake is that we had vertical arrays. That means we have a very detailed soil profile. We measured everything almost that can be measured in the laboratory and in the field. The idea is to see how it is affecting. We now have 3 vertical arrays. That means we have instruments, for example, 140 meters, then 75 meters, 50 meters, and on the ground surface. You can see the amplification of the earthquake waves starting from the bedrock, going all the way to the top. This was a vertical array where we had the soil thickness around 140 meters, and now we have another one which is actually deeper, and it starts from 288 and it goes all the way to the ground surface. As you can see now, the predominant period shifted significantly. Now we have a predominant period in the order of 1 second. Since this earthquake is coming from 180 kilometers away, the high frequencies are lost by the time they reach to Istanbul. Now, we can see from these small examples that site amplification is a fact. We can measure it. Now, how are we going to deal with this problem? So what are the basic factors? And how can we proceed? So one suggestion from here is that let us look at the general picture. In the general picture, we see that we have a bedrock, and it ruptures somewhere, and then all the waves travel to the soil layers, and we need the motion on the ground surface in order to design our buildings sufficiently safe enough. So taking this into consideration, how can we proceed? We are interested, first of all, what is going to be the rupture, and where it is going to be the rupture, and when it is going to be rupture, but that problem is a very ambiguous problem. We can only use probabilistic approach. We cannot predict the earthquakes, but we can come up with a probabilistic approach based on the history, and we can come up with logical numbers that would affect our area in the long run. Now, here, there is 4 levels of analysis. First is regional hazard. What I mean by regional hazard is something like this. This is actually a regional hazard investigation conducted by Professor Erdik and his colleagues, and this hazard should be in the order of 1 to 5,000 or 1 to 10,000 maximum. The idea is to determine, for example, in this case, variation of these design spectra, uniform hazard spectra we call it, uniform hazard spectra on the ground surface, so that we can design our buildings according to that. And as you see in this mesh in the Bakırköy area, it is 250 by 250, and it is changing every 250 meters. So in order to be on the safe side, to build new buildings or to assess the vulnerability of the old buildings, which is also very important in cities like Istanbul and in Zagreb, where you have large number of old buildings. So the idea is we should be able to have this uniform, this is a uniform hazard spectra on the outcrop, on the bedrock, obtained by probabilistic hazard study conducted by normally engineers and seismologists. Now, the other issue that takes into our field is site characterization. As a geotechnical engineers, we have to take care of the site characterization. That means we have to have the properties and thickness of the soil layers, dynamic shear modulus, variation of shear modulus, and of course, the bedrock. The depth of the bedrock for us in terms of earthquake engineering is a very important issue. And if you look at typical soil profiles, you can see that we go all the way down until we reach the bedrock based on borings or geophysical tests, so that we know, for example, here we have, these are some of the borings in Istanbul. Here, as you can see, some of them is 90 meters, 110 meters, and even 160 meters. Of course, we didn't drill all the way to 160 meters. In few occasions we did. But you cannot do that. It's a very expensive, very time-consuming. But you have geophysical investigation techniques. The top part, the top 30 meters or 40 meters, can be determined based on borings. Has to be determined based on borings. Now, if you look here, this is a typical profile, and this is actually what we mean by degradation curves. You have to determine the degradation curves for dynamic shear modulus and damping. And as a result of that, then you would be able to analyze how the soil layers would behave during a possible earthquake. Now, the last part is 1D site response analysis. This is the simplest approach. Of course, we can do, if necessary, 2D or nonlinear or effective stress analysis. But 2D total stress analysis would be sufficient in most cases, like in Istanbul. We modified the SHAKE program that was produced in 1970s in University of Berkeley. Was very efficient program in 1970s, but since then we have learned many things. And one of the things that we have learned that the site amplification is a function of the frequency of the earthquake. So now we have to modify the program, take an empirical approach that was developed by Japanese colleagues and insert it to our program, and we also modified the program to be more stress dependent. Now, how is the result? This is the recorded motions in Istanbul during the 99 earthquake. And here, if we go, we have 4 stations. At that time, we had limited stations, and we recorded, as you see, the maximum of 17% G. And we had damage in Istanbul in certain areas. Now, this is the profiles for 3 stations that I mentioned, vertical arrays, or at that time, we had surface ground motion recorders. Then we try to see what is happening. This is actually what is recorded during the earthquake. When we use the classical shake without any correction, we'll get some fit. As you see, in the north-south, the fit is not so bad, or modeling, but in east-west, it is not so good. So we improved, we made it, included stress dependency into the program, and our fits have improved. We added the frequency dependence, our fits improved more. So that means, even in this case, when we have the bedrock motion somewhere in Istanbul, we modeled how to get the ground motion at the ground surface, and you can see with the available 1D simple shake model, we would be able to come up with a logical result. And even in terms of acceleration time history, the upper one is the one that is recorded in reality, and the bottom ones are that has been modeled by shake. Now, what is microzonation? Now we see that microzonation is an essential ingredient. So microzonation, the objective is first to improve the urban planning, to put our important structures in areas where the ground shaking intensity is as low as possible. If we have buildings in high ground shaking intensity areas, then we control them, we design them accordingly. And of course, this will help disaster preparedness, and of course, it will be mitigation of hazard. Now, we have already seen that regional hazard in urban scale and estimation of earthquake characteristics on the ground surface, this is also a part of the job. And then we have comprehensive assessment of the building vulnerability. Now, there are a large number of microzonation research papers published everywhere. And they have taken different properties, for example, with respect to peak ground acceleration, with respect to Arias intensity, or spectral intensity. All have been tried by different researchers. We adopted a different procedure, slightly different procedure. First of all, we thought that we need to combine 2 factors. The first factor is a very empirical ground response analysis that was conducted by Borchard and his colleagues. It is based on VS30. VS30 is the average shear wave velocity at the top 30 meters. You take the layer thicknesses and the velocity of each layer and take the weighted average, and you come up with a number. And this is what is being used in Eurocode, what is being used in NEHRP, and in some of the codes in other countries to determine the site effects. So this is an empirical procedure, but it is based on actual data observed in California, based on the instrument recordings, and based on the VS measured. So there's an empirical correlation, even though it has some irregularities when you apply to the site conditions, as I showed you in the beginning. The second one is the site response analysis. Site response analysis is a mathematical tool. It has certain advantages and certain disadvantages. All numerical tools are a function of what you put inside as a parameter. And sometimes we may not be putting the correct parameters. So therefore, it has to be included somehow. We took the spectral acceleration from 0.1 second to 1 second. This is where most of our buildings are. And summed that up and actually used both parameters in a manner that is justifiable, so that we were, as I will show you a little bit later, we overlap these 2 maps and come up with a final microzonation map. But there was one other problem if you use one parameter and absolute values, because microzonation is not going to be used by civil engineers who understand earthquake engineering and who would know what PGA would mean, but it is going to be used by city planners and architects. I love architects, but architects have a limited knowledge about earthquake engineering, which they should have in the long run. So we decided that instead of giving them numbers, we should give them some limits. And here, in terms of cumulative distribution, for example, this is the average spectral acceleration that we compute from site response analysis. We divide it into three parts. Zone C, which is the dangerous part. Zone B, intermediate part. Zone A is the most safest part. So if we do this, for example, if we take one part of Istanbul, this is a pilot study that we have conducted. This is Zeytinburnu, one of the very close to the Eminönü, and it is very dangerous area because if we have the next earthquake, this is one of the areas that is going to be damaged significantly. And what we did site response in each cell, and as you see, when we did site response analysis, we used a lot of records, as I will try to show you a little bit later. We use a lot of records so that we make sure about the variability of earthquake input. And here we have drawn the average and drawn a best fit and used that area, that curve, that spectra as the output. Here, with respect to these two parameters, on the left you can see that we divide according to the VS30. The whole Zeytinburnu can be divided into two categories because the difference is not so significant. So we have good parts and bad parts. But in the case of site response analysis, we have three parts, A, B, C. What we propose is to join them, overlap the map, and here we have the final microzonation map for Zeytinburnu. Zeytinburnu is composed of 231 meshes of 250, 250 in size, so that we can play with that with other parametric studies. What I want to show you, what is the importance of the microzonation with respect to the material parameters involved. This final result involved using 22 records for each cell, and we had borings in each cell. So this is the final version of the microzonation for Zeytinburnu. But before Zeytinburnu, you can see that here the importance of site investigation. On the left-hand side, you see we did a microzonation in Zeytinburnu before all these microzonation study Istanbul was conducted. It was based on limited number of borings and limited number of input motion. But you can see that with the age, with the increase, even the geotechnical data in both are same, but the increase in the input acceleration during the site response analysis would make a significant difference. And the other issue here is that if we have much more detailed site investigation, the situation changed also radically. Now, one of the problems is the vulnerability or the return period, the frequency. Normally in the buildings we design with 10% probability of exceedance in 50 years. That means the return period is 475 years. But sometimes as a result of the electronic devices that we have in the houses or the hospitals or the schools, we cannot live with that return period anymore. So one option for important structures is to go to 2% exceedance in 50 years, which is corresponding to 2,475-year return period. And if you see, when we do the zonation by increasing the return period, we have a different zonation. So therefore, as a city planner, you have to take into consideration what is your goal. Do you want to actually lead to normal buildings, or would you like to be interested also in high-risk buildings? And here, as I show you, if you choose different parameters like spectral accelerations or PGA or PGV, your microzonation maps will be different, especially if you take into consideration the peak ground velocity, which is one of the controlling factors that control the damage of the lifeline systems. You should be taking into consideration maybe PGV microzonation. Now, this is the end result of the OYO study. As you see, with respect to Istanbul, with around 3,000 borings and 3 years' work, we come up with a microzonation map of Istanbul in terms of three categories. The red zones are the dangerous zones. So if you have a school or a hospital in those zones, they have to be retrofitted, they have to be controlled. If we are going to build anything there, it will be designed very carefully, taking into consideration possible effects. For example, in Turkey now, all the hospitals are being built on seismic isolators. We can also plot PGA. This is the result of the PGA, and you can see that PGA goes all the way from 0.5 all the way from 0.7 to 30%. So the scatter or the variation of peak ground acceleration within the city can be radically different. Now, what is the end result? What am I going to do now? Now, the damage scenarios is, can I make an estimate of what may happen to Istanbul? Now, of course, we have seen earthquake source characteristics, site response, and now the structural features. We have to have a building inventory, and we have to have a vulnerability relationships. Now, we had this scenario was conducted way back in 2005 or 6. We had a building inventory based on structural systems, the age, number of stories. It's a very simple building inventory. We can improve, or we are improving the building inventory, because that will determine our vulnerability. Here, the types are limited, reinforced concrete or shear wall building or prefabricated buildings. With age, we have, with number of stories, we have from 4 stories, more than 8 stories. And of course, with respect to construction year, at one point of time in 1973, we had an earthquake code, so we considered that as a division, and we have established also post-construction 1980, we had another earthquake variation in the earthquake code. And if you do that, at that time we had a limited number of, these are reinforced concrete buildings. We had around 562,000 buildings. It was distributed, as you can see. Now, within the city, they are located like this. This is the Istanbul big metropolitan. Now, the mesh size is 500 meter to 500 meter. You can see that in some locations, we have a very dense settlement. And now, let's see what happens. So first of all, we have to have a damage scenario, taking into consideration all the capacity spectrum, inelastic deformations, and then we utilize the cumulative and discrete damage, and we classify the damage into 5 categories: no damage, slight damage, moderate damage, extensive, and collapse. And this is some of the vulnerability curves that we used to determine these vulnerability curves. Of course, changes from the building type to the other building type. And you can see here low-rise RC buildings and low-rise post-1980 buildings. So the vulnerability, depending upon the selection, changes. And at this point, we had a big project with European project. It was related to the earthquake scenarios in Istanbul, and we had a colleague, INGV, so we made a deterministic study. This is what may happen to Istanbul. As you have seen, now we have 2 faults that is not broken yet. The problem in Istanbul is that last time, in 99, it almost broke all the way to here. North Anatolian fault is a very well-behaved fault. It started to rupture from eastern Turkey in 1938, and since then, it is rupturing toward Istanbul continuously. The last rupture was in 1999. So they estimate that in the next 30 years, starting from 1999, that we may have an earthquake. And it may be a major earthquake. So this is the 2 big faults. And let's see what happens. This is a mathematical modeling of damage scenario in a deterministic manner. So you can see now this rupture. Of course, there are very irregularities or unknowns. We may know that this fault is going to rupture, but where is the rupture going to start? Let's assume it started on the very west and propagated toward east. As you can see, these are some of the mathematical results obtained. The mesh is 5-kilometer mesh. You can see how the earthquake excitations would change. What happens if it breaks in between? It's a biaxial rupture. And here you can see the variation of accelerations in different parts of the city. And this is, again, uniform rupture now toward west. And you can see that depending upon the rupture, things can be radically different. Now, this is one of the results of these, one of the worst results from these scenarios. And you can see that this is the spectral accelerations at short period, and as you may be able to read, it changes from 3G all the way to 0.5G. The design code in Istanbul spectral acceleration-wise, until this year, has been only 1G. So you can imagine what may happen if we have this earthquake. And here, this is the number of collapsed buildings in each square within the city. And this is going to be like 160,000 buildings, 10,000 medium, 4,000 extensive, 91 will be totally collapsed, and it is estimated that we will have in the order of 150,000 casualties. Now, how can we do that? So we have to do a lot of parametric study, and we developed a model called coherent loss. Of course, now they have a better version, and it starts taking into consideration the seismic hazard and geotechnical conditions. It inputs the earthquake characteristics ground series. Then we develop the new herp envelopes, and then we determine the microzonation maps, and then based on the building inventory, we can determine the damage distribution. This is a computer program that doesn't require something new. It is a very simple programming skills, but now we have, of course, everywhere in the world, they have a lot of programs. Here, one example. We did a very detailed study in Zeytinburnu, the city I showed you previously. And here, we have a very detailed building inventory. There was about 16,000 buildings here. All of them were evaluated in a very detailed fashion, even on a building plan. And you can see that we have the B represents masonry or reinforced concrete. And if we do the damage study for Zeytinburnu, you can see that we will have some areas which will be very susceptible to high damage. In Istanbul, in Turkey now, we have a rehabilitation law. That means if your house is somehow considered vulnerable during an earthquake, the government has all the power to demolish it. So a lot of old houses or vulnerable houses are being demolished in Istanbul and new ones are built. Of course, between you and me, I'm not very sure if we are building safer buildings. And here, based on the 16,000 buildings, the damage was like 2,444 collapsed buildings. And that is relatively high if you consider that the total number of buildings is 16,000. Now, as a last item in this probabilistic study, the procedure I explained is always in terms of site response. There is always a faster procedure, and this is based on VS30. This is the NIHERP procedure. And if you look at the both of them together, that NIHERP, the simple procedure, is not giving very high results. So it may give a false feeling that you are on the safe side. But it is necessary to take into soil conditions into effect, and it is necessary to take possible earthquake characteristics variability so that you can have a better understanding. So this is what I was suggesting. Earthquake-based regional scale is very necessary. Large number of hazard-compatible. Somehow I seem to have jumped over them. Large number of earthquakes. Since I may have some time, let me go back. I think I jumped over some of my slides. Where are they? Oh, here. Now, this is an important part of the microzonation, which I forgot. I don't know how I jumped over it. When we are dealing with number of earthquake inputs to do site response analysis. In some earthquake codes, you are only required to select 5 input motion. But here we did a parametric study. We selected, as you may see, 5 input, 10 input, 15 input, 20 input, 22 our design, and 25 input. As you can see here, with the increase of the number of inputs, you get an average which is much more representative, taking into consideration the variability of our ground motion. If we go one step, this is, for example, the input ground motion that we selected for site response. You can see the variability of the recorded motions. These are from all over the world. What we mean hazard compatibility is they are from the same rupture type, same distance approximately, and same magnitude range. And if we want to go one more step, you can see we have to also do scaling. Take the record from anywhere else, which fits to this hazard compatibility, and then scale it such that the black line is your target spectra that you obtain, or outcrop spectra, but you have to take that into consideration to do site response analysis. And you can see the best, we also try different scaling procedures, and the most appropriate scaling procedure, which is also suggested in ASC 7, is to scale each record to fit the target spectra using an optimization technique. So this is one way of doing a site response analysis, taking into account all the variability, all the possible variability that may occur as a result of the earthquake input. And as you can see, if I plot them, they are all slightly different. Now I go to my last slide. And here, large number of earthquake inputs are important in one sense, as I demonstrated, and large microzonation with respect to average spectral accelerations and site response analysis is appropriate system. 3 relative levels, high, medium, low, is understandable by everybody. Detailed site characterization is a very important issue. There are differences between Nieherr formulation, this VS30, and there can be significant differences among the probabilistic and deterministic scenarios. So with this, I go to acknowledgements. There has been many people who worked on this project, and I would like to express my gratitude to them. And my last slide, the end. Thank you very much.